Among energy filters, there's two classes. There are what are called post-column filters, and there are in-column, or sometimes called omega filters. So the post-column filters, you have your whole microscope column, and often, there's the viewing chamber here that'll let you see what's going on. And then following the column, the energy filter is a prism. And the detector is at the end of that prism. And somewhere after the prism, there is a slit. We'll call it the energy slit. And the principle in operation is that electrons that are coming down the column at, let's say, for example, 300 kilovolts, those that are either unscattered or elastically scattered emerge with the same energy, the full 300 kilovolts. And they, as they pass through this energy prism, are bent and allowed to pass right through the energy slit, and they come and hit the detector and form the image. On the other hand, electrons that, after they hit the sample, are inelastically scattered and emerge at lower energy, perhaps 20 eV lower, perhaps 100 eV lower. As these go through the column, because they're of lower energy, they are bent more strongly by the prism. They hit the energy slit and are absorbed there and are removed from the image. The in-column filters can be drawn like this. So the detector is at the bottom of the column, and the electrons, after they are scattered by the sample, are bent, their pathway is bent into the shape of an omega, and then sent on to the detector. Here again, there's an energy slit positioned so that electrons with the full incident energy pass through the slit onto the detector. But again, electrons with lower energy, because of an inelastic scattering event, these are bent more strongly by the filter, and they're absorbed either in the walls of the filter or on the energy slit and are removed from the image. And it's the shape of this that gives it its name of an omega filter. Now, in both cases, there's the possibility of removing the slit altogether. Or if the slit is in, it's possible to choose the slit width. Typical values for cryo-EM are 20 electron volts, because most inelastic scattering events remove more than 10 eV from the incident electron. We could plot, for instance, the energies of the various electrons coming down the microscope. And for instance, if that was 300 kV, depending on the temporal coherence of our electron gun, we would see a very tight peak of electrons all focused around 300 kV. If a sample's inserted that's electron dense and there's a lot of scattering, then the curve might be fewer electrons coming through at 300 kV and a tail of electrons coming through with a number of lower energies. Here I've drawn it to the right as lower, but these would be higher energies and these are lower energies. And so as inelastic scattering events happen, these electrons emerge with lower energies. And so we can control whether the slit is in or out. We control the slit position, and we control the slit width. If we were to place the energy slit right at centered at 300 kilovolts, and give a width of 20 eV, for instance, if that's 20 eV, we would then allow the passage of the elastically scattered electrons, the unscattered electrons, and just a few of the inelastically scattered electrons. But the vast majority of inelastically scattered electrons would be removed from the image. Now, it's also possible to set the position of your energy filter here and make the width whatever you like, of course. There's a lot of possibilities. And in fact, you can even do spectroscopy by producing an image using just electrons that have lost a certain amount of energy. And this can give you information about which elements are present in your object in which positions, because each element will cause characteristic losses of energies. But most commonly, we center the energy slit at the incident energy of the electron beam and use a width of usually 20 electron volts.